This video is for class 8 physics and we are starting the chapter energy. Before discussing the main topic energy, it is very essential to understand work. So, you people can go to page number 60 and refer your book. So, I am starting work. In everyday life, all of us do some work. We do work when we play, when we go to school, when we go upstairs, when we pedal a bicycle, and when we lift a load, and so on. In common language, we use the word work much casually. For example, if we push a wall, we say that work is done by us because we get tired. While reading a book, we say that we are working, but actually no work is done in these activities. Let us understand why no work is done in these activities. In physics, the word work has a special meaning. Work is said to be done only when body changes its position. That means it starts moving or moves on the application of force. That means a force has to get applied on it. So no work is said to be done if there is no motion produced in the body even when a force acts on it. Thus, work is said to be done if the force applied on a body moves it. If no motion takes place, no work is said to be done even if you apply some force. For example, a cyclist pedaling a cycle. A cyclist pedaling a cycle does work. How? Now listen, the cyclist is applying a force because of which the cycle is moving. Hence, cyclist is doing work. So whoever is applying force, that particular thing is doing work. Now the next example is a horse pulling a cart. Here the cart moves and horse is applying the force. Hence, horse is doing the work on the cart. Next thing, an engine pulling a train does work. So here engine is applying force, hence engine is doing work, but the train is moving, so work is being done on the train. A coolie lifting a box does work. Okay, so the box is being moved by coolie, so coolie is applying force, hence coolie is doing some work on the box. A boy going upstairs does work. So the boy is lifting his own weight. So boy is applying force. Hence boy is doing some work. A boy lifting on himself, right? A boy lifting a book does work. That means the boy is applying the force. Hence he is doing some work on the book. So if you can see this picture, right, lifting the book, so you can see here the work is being done on this book, and who is doing the work? The boy is doing the work. So who does the work here? Boy does the work. And on whom the work is being done? The work is being done on the book. Okay, so now we can go to the next page. Coming to the next page, page number 61. When a crane picks up a car involved in an accident and takes it to a workshop, we say that work is done, right? Because the crane moves the car. In a school playground, while playing football, when a boy hits the ball and runs towards the goal, we say work is done because there is motion and force. A boy climbing upstairs does work because he is lifting himself up. So work is also done by a force if the force applied on a body changes its size or shape. For an example, if a boy squeezes a toothpaste tube or gum tube or a rubber ball, he does work in changing the shape of the tube or ball, because here also we can see force and displacement, right? So work is done in changing the shape and size of the ball. Similarly, a boy does work in stretching a rubber string, in which size of the string increases. So a person does no work if there is no change in position or no motion. after the application of force also. For example, a boy pushing a car or a heavy stone does no work if the car or stone does not move, although he may get tired. So where will the energy go? Last time we had discussed, so I think you know the answer. A person pushing against a wall also does no work since he is not able to move the wall. Similarly, a coolie does no work while standing with a heavy box because this time the box is not moved. As there is no motion, although he may get tired holding it, but the coolie does work when he raises the heavy box to his head. So you can see here in all these examples there is motion and force involved. So basically here in these 2 pages what we learn is that work depends upon 2 things, which is force and displacement, force and motion. Thus following 2 conditions must be fulfilled for work to be done. Number 1, a force must act on the body. If there is no force, no work is done. The second condition is the force must produce a change in position, that is motion, or it should be able to change the shape and size of the body. Okay, so basically there are 2 factors that affects the work done. So factors affecting the amount of work done. Experimentally, it is found that the amount of work done by a force depends upon the following 2 factors. Number 1, magnitude of the force applied and the distance moved by the body in the direction of force. So there are 2 factors which affects the work done. Number 1, magnitude of force applied means how much force you are applying. Magnitude here means how much force you are applying. And number 2, distance moved by the body in the direction of force. That means suppose you are pushing a chair towards a wall. That means the distance, the chair also should move towards the wall, right? Because the direction of the distance and the force also should be same. Actually the distance along with the direction is known as displacement. We had done in class 7. So basically the 2 factors are force and displacement. So now I think you are able to tell me how does it affect the work. If you apply more force, more work should be done, and if it moves more distance, more work should be done. Okay, sorry. So number 1, dependence of amount of work done on the magnitude of the force applied on the body. Work done is more if the force applied to move the body is more. Obviously that is common sense. If you apply more force, more work should be done. More work is done by us if we lift a bucket full of water from the ground floor to the first floor than if we lift an empty bucket to the same height. The reason is that we have to apply a greater force to lift the bucket full of water than to lift the empty bucket. The second factor, dependence of amount of work done on the distance moved by the body in the direction of force. Work done is more if the distance moved by the body in the direction of force is more. So more work is done by us if we lift a bucket of water from the ground floor to the second floor than if we lift the same bucket of water from the ground floor to the first floor. Okay, I hope you understood this, right? Now we can go to the definition of work. We define the work done as follows. The work done by a force on a body is equal to the product of, that is multiplication of, force applied and the distance moved by the body in the direction of force. So work done is equal to force into distance. So work done is equal to what? Force into distance. So this was the formula that I was talking about. So you can see here in figure 4.7 here, right? So let a force F be applied on a body which moves it from a position A, here position A, this one, to the position B, this one here. So by a distance, so it moves a distance d here, right, in the direction of force. Then the work done by the force on the body will be W equals to F into D, right? Suppose the force is 10 Newton and suppose the distance moved is 2 meter, then the work done should be 10 into 2. Then the work done should be 10 multiplied by 2. So we should get 20 as our answer. So this is how we can calculate work if we know force and distance. Now obviously if a force acts on a body and the body does not move, suppose you are pushing the wall, since the distance is 0, since the d is 0, so w is also should be 0. Okay, I hope you understood this. Now this box, do you know box? The work done by a force is 0 if the body moves in the direction perpendicular to the direction of force. For example, when a stone is tied at the end of a string, is reeled or moved in a horizontal circular path, the motion of a stone is always normal to the force of tension. Okay, here they are trying to use the word normal. Normal means perpendicular, 90 degree to the force of tension in the string as shown in the figure. Therefore the work done by the force of tension on the stone is 0. Okay, let me try to explain this. So what they are trying to say is, suppose you tie one stone here, okay, and you are holding it with hand here, and this is the string. Okay, this is the string, right? It is string, string, right? This is string. So when you try to move the stone in a circular path, right, so what happens here is the motion at this point is in this direction, right? The motion of the stone is in this direction and the force is in this direction because you are trying to pull it inside. So the angle between these two is 90 degree. Under this scenario, work done will be 0 even if there is distance and force. Even if there is distance and force, still the work done will be 0 whenever there is the angle, whenever the angle between the distance and the force or the displacement and the force is 90 degree. This you'll understand more in class 10. So now similarly in motion of earth around the sun, the force of attraction on earth by the sun is always normal to the direction of motion of the earth. So no work is done by the gravitational force of the sun on the earth. And then similarly when moon goes around the earth, right, earth does not do any work. The gravitational force of the earth does not do any work. Similarly, if a coolie moves on a plain road with the luggage on his head, the work done by him against the force of gravity is 0, since distance moved by him is normal to his weight. Okay, let me try to explain this. Okay, suppose this particular person is carrying load and starts moving front. Yeah, suppose he starts moving front, right? Where is the gravity acting? The gravity is acting downwards, right? So what is the angle between them? Again 90 degree. So I hope you understood. The person is moving front, right, whereas the gravity is acting downwards. So the angle between them is again 90 degree. So whenever the angle is 90 degree between force and distance, this is distance, this is force, right? Whenever the angle between distance and force is 90 degree, what will be the work done? The work done should be 0. I hope you understood this. Coming to the last part of the video, units of work. We have read that the SI unit of force is Newton, right? SI unit of force is Newton and that of distance is meter. Hence, the SI unit of work will be Newton into meter, which is Newton meter. So, to honor the scientist Joule, we also use Newton meter as Joule. So, the unit Joule has been named after the name of the scientist James Prescott Joule. So, now the definition of Joule. Since 1 joule should be equal to 1 Newton into 1 meter, 1 joule should be equal to 1 Newton into 1 meter. So, therefore, joule can be defined as 1 joule of work is said to be done if 1 Newton force when acting on a body moves it by 1 meter in the direction of force, here in the direction of force. So 1 joule of work is said to be done when 1 Newton of force when acting on a body moves it by 1 meter in the direction of force. Let me try to explain this. Suppose there is one object, right, and somebody is trying to push it with the force F, right. Let that force F be equals to 1 Newton, and after the application of force, this object rolls down and covers a distance of 1 meter. So in that case, how much work is done by the force? The work done by the force will be 1 joule. I hope you understood this. If 1 Newton pushes the object and the object moves by 1 meter, then the work done is 1 joule. Bigger units of work is kilojoule, symbol is kJ, megajoule, etc. So if we measure the force in kgf and the distance in meter, the unit of work is kgf into meter. So 1 kgf has nearly 9.8 joule, right? So this is how this 9.8 comes. We will try to understand in class 9. So in chapter 3 we have learned that the unit of moment of force. Okay, we have left this moment of force in the chapter 3. If it is required, then only we'll be doing it. Okay, so the moment of force also has the unit Newton meter, but which is not joule. Okay, so please remember that. So till here it's important, right? Till here. Okay, the other videos about energy I shall give you afterwards. Thank you so much.